Okay, hey everyone, am I audible to everyone? Welcome to the fourth class in this course. So my name is Nanda and today I'll be giving a short lecture and demo on how you would actually tackle the Verilog problems in this course. And this is meant to be like a brief tutorial on Verilog and system Verilog as it pertains to this class. And over the course of the lecture, you will see the kinds of designs, operations, and blocks that you will be working with. And also, it'll basically cover in brief like how you can actually write synthesizable Verilog code. And then once you actually write the Verilog code, how do you run synthesis so that you can get the performance, power, and area, or PPA for short, to measure what is the quality of your code. Okay. So for those of you who have taken the 5327 class or are parallelly taking it, some parts of this will overlap, but you do not need to take that class to do the assignments for this course. And hopefully this lecture, this presentation here, should be enough to give you enough context so that you should be able to work out any of the problems in this class. Okay. So what is Verilog? So Verilog is a hardware description language. So one thing which I wanted to clarify immediately is that I sometimes interchangeably use Verilog and system Verilog. So in reality, system Verilog is just the superset of Verilog and it's the current version of the standard. So if I interchangeably use the two, don't get confused. And so now what exactly is a hardware description language? So it, like the name itself states, is that it's how you can actually describe the functionality of hardware blocks. Like for example, if you want to describe the functionality of an adder or a multiplier, this is how you could describe that functionality within code in a way that a tool can understand what you intended and then it can create hardware out of that. So, and this kind of a system is a lot more simple to design and use, and it's also a lot more scalable. So you can design very small blocks like adders or multipliers, or you can design like billion gate blocks like processors. So why do we need HDL? So the question is really, the answer is really simple, is that when we are actually making more complicated systems, we need a systematic approach to design from the smallest blocks, and also an easy way to integrate all of these blocks together to make up larger blocks, right? Because in reality, these digital systems are quite complex with a lot of submodules and interactions which need to be accounted for. Then the other reason is that it allows for you to have a very high level of abstraction. So what that essentially means is that you do not need to go down to the bare metal level of saying like what gates and how these gates interact with each other, but then you can keep it at some levels of constructs which will be easier for the programmer, so it will be easier and quicker to design these modules. And lastly, it provides like a standardized interface to your actual tools, like for example, your synthesis tool, your verification tool. So that way it can understand the codes you do and it can easily translate that into hardware. So as you can see, the system Verilog or Verilog has taken many iterations or evolutions over the years. So this is just an example of the different different modules which are actually added to Verilog as it was going on. And right now it's showing 2012, but the latest iteration of system Verilog is actually 2017. So one common misconception is that system Verilog, so Verilog is for design and system Verilog is for testing. That is actually not true, and because one thing for fact is that system Verilog is a superset. So anything you can do in Verilog, you can do in system Verilog. But also system Verilog is actually designed for, it's also made to simplify the design process as well. And over the course of this tutorial, you'll also see some of the unique things to system Verilog which basically aid and implement design. So this should give you a bit of an overview of what the language is, what you're working with, why are we doing all of this. So now the question is, you're given a design, right? So how do you actually go about like process? Let's say we give you a homework question which says design this sort of a filter. What is the different ways you can approach this problem, or what's the different ways you can implement it? So this is where you can, based on how you design the problem or like the way it's done, you can have an approach which is either top down or bottom up, or you can have definitions based on the level of abstraction at which you write your code. So when I say bottom up design or top down design, what do I actually mean? So the way you can think of a top down, a bottom up design is that you initially design the most basic leaf units of your design. So for example, you would design like let's say half adders, full adders, and then after you have multiple half adders, full adders, you put those together, those leaf cells together to make an adder, or you use those leaf cells to make a multiplier. And then now with an adder and a multiplier leaf cells, and with let's say a registered leaf cell, like a delay element, you put all of those together to design a filter, right? So that's kind of like a bottom-up approach. A top-down approach where you can think of is that you first look at the problem as a whole and then decide which like logic gets divided into which sub-blocks. Right? So let's say, for example, you're designing some kind of a CPU or a processor. At the top level, you know, okay, we need to have some RAM, we need to have some we need to have like a arithmetic logic unit, we need to have some cache memory, we need to have let's say a pipeline for a pipeline stages for the processor. So then you kind of break down the functionality into subblocks, you further break down the subblocks till you finally reach a bunch of leaf cells, right? A lot of what we do in this tutorial and what you'll do in this course is we'll try to see, once we we're given a problem, how do you break it up into smaller blocks and then implement it in Verilog. So this will be kind of the majority way we'll be talking about any sort of design here. So now, based on what is the level of abstraction, there are different ways you can use Verilog or system Verilog. So the first way is behavioral. So behavioral is essentially designed to be like the highest level of abstraction, where you represent all your code at like an algorithmic level. So for example, what that would mean is that, let's say you're implementing an adder. You would literally write a code along the lines of A plus B, right? You do not go down into the details of how an adder is implemented. You do not go into a lot of the details of what are the connections, what are the sub-blocks, but rather you leave it at an algorithmic level and let the tool interpret it and design it for you, right? So another very simple example would be if you're implementing a multiplexer. So a multiplexer, if you can think about it, is in a algorithmic way would be like an if-else statement, right? If its condition is 1, do this. If its condition is 0, do this path, right? So the second level is something called register transfer level. So what it actually means is that you transfer the information between different registers. And while you're transferring it, you do sort of logical operations on it. So registers are essentially states or memory locations within in your Verilog code, or like you could say, think of it as variables in your Verilog code. So just that when you are when you're processing the information, you would use logical operations to say, for example, if you want to do an AND gate, you would just say A is equal to B and C, right? Or if the same example, if you want to implement a multiplexer, Verilog has something called a conditional statement, which is another kind of a logical operation which implements that. So this is meant to be an intermediate level of abstraction. So at the lowest level of abstraction, we have something called structural. So structural is where you go to the bare metal. You're saying that it is made up of these gates. So you would actually implement your multiplexer in the form of gates like AND gates, OR gates, and NOT gates, and so on and so forth. And I'll give you some examples of this in later on. So So if you're not able to imagine it now, it'll be more clear towards the end. So these are the different levels of abstraction in which you can design your code. So what is the actual process of designing? So here you can have kind of like what is the design flow, which you will see most often in this course. So at the top level, you have something called a specification. So in this case, you can imagine your specification is something like the homework problem you're given, or like a project description for your final project in this course, right? It specifies like what is the inputs, what is the expected outputs, or like what is the function to give the expected output, right? And pretty much like some kind of a constraints, that it doesn't have an area constraint, does have some power constraints or things like that. It just specifies what are all the parameters of your design. So now once you actually have the design, like you have the specification, the next thing which you have is the high level design, which is essentially, if you think about what you have done till now, this is your data flow graph, right? What are the different operations in your code? How do those operations interact with each other? So implementing a data flow graph for your specification is kind of like a high level design. The low level, like my microarchitecture design, would be actually trying to implement it at the circuit level. So you would have seen the circuit diagrams which actually show an adder, a multiplier, these delay elements, or these like switches, right? So that's kind of like a circuit level implementation, which is like your lowest level of detail which you can represent in a diagram. And now that you actually have the circuit element, you actually code your RTL, as simple as that. Once you code your RTL, we need to verify first if your design actually works, because there's no point basically sending out the design if it's not going to implement. Like, what's the point of an adder if it does not add two numbers, right? Or in a worst case scenario, if it actually adds and gives you a wrong result, have you checked all of the condition, like all the corner conditions? Like, for example, does the adder overflow? Does the subtractor underflow? So things like that are what you should handle in verification. And finally, you have synthesis. So synthesis essentially takes whatever you have designed in Verilog and converts that to real life hardware, right? So if you have written the code for an adder, it will actually instantiate an adder with all of its gates and connections within your hardware block. So now that we actually have seen what's a design flow, I thought I'll go over some of the like key Verilog syntax which you will see throughout this course, and which you will need to make use of. So the main building block of your designs will be modules. So the way you can think of a module is it compartmentalizes your logic into a kind of a functional block, right? So the way you would think of it is that if you're building an adder, like let's say you're building an 8-bit adder. So each bit will have its own full adder, so that will be one module, and then you'll connect multiple full adders together to make your 8-bit adder, and so that will be another module. So in this example and in future, in all these examples, we're going to be working with a simple FIR filter. So in this case, if you actually look at the syntax here, let me see if I can get a highlight. Yeah, let me see that. So if you look at the syntax here, you have your basically a module name, which is defined over here. So we are calling it we are naming it an FIR filter, and then you need to actually define what are the input and output ports. So the way you'd imagine it is that if, let's say you're working in like one of these circuits lab, right? You'll have a breadboard and you have these ICs which you put onto the breadboard. So when you use the IC, the pins of those ICs are predefined, right? You may not know what's happening inside, but you know that these are the pins which exist in the block. So it's a kind of a similar concept in modules and its port declaration. You're kind of just saying this is the top level module, and then these are all the pins which actually connect to that module. So if you were to use this module somewhere else, this is kind of the limit to which any other block which would sit on top would actually see in this module. So this is about the declaration. So now we have something which can aid us, which are called parameters. So when you think about parameters, the first thing which should come to your mind are these are just constants, right, which are basically set for this particular block and do not change like for the lifetime of this block. So the way you can think of it is, so if you see this like the constants in this example, this is saying that it has a data width of 8, a coefficient width of 8, output data width of 20, and number of taps of 3. So when I say width, that means the number of bits in those in the data, in the coefficient, and in the outputs. And the taps are saying the number of filter taps in your system. So as you can imagine, like what is Verilog actually doing, right? Like whenever you think of Verilog, and I'll kind of say reiterate this multiple times, is you should always imagine that you're actually designing something physical. This is not meant to be some kind of a coding language, right? It's very easy to get back into the world of Python or C++ and think everything is some kind of a code which you just have to design logically. But whenever you're like writing in Verilog, the first thing you have to do is you take a step back and say, how would this be represented physically? Like if I had to convert this code to a physical block of hardware, would that be realizable? And that's essentially the question which you need to keep answering as you do your design. So in this example, what is a parameter? So a parameter is just saying that right at the beginning, when we are synthesizing the code, we have kind of fixed that this is what the code is going to look like. So we are going to say that in this case, let's say data width of 8. It says that there are 8 bits in our register, and every single place where it's used will be 8 for the duration of whatever, of not exactly duration, it's like something like permanent, right? So if you make an 8-bit adder, it's always going to be an 8-bit adder. So that is what's the significance of parameters, what's the usefulness of it? Well, it allows you to create multiple such blocks with slightly different configurations. What that means is, let's say for example, in this case you are using a 3-tap filter. Let's say you need to use both a 3-tap filter and a 5-tap filter in your design. Does that mean you rewrite your code to just to change one line of code and say instead of 3 make it 5? Probably that's not a very efficient way to do it, right? So if you're changing some hardware aspects of your design, you define those as parameters so that when you instantiate the module, you can just change the parameter when you instantiate it, and then it will take the new parameter for the new block. So then for the same code, you can have both a 3-tap filter as well as a 5-tap filter.
But they will be separate files.
They will not be separate files. They'll still be one file.
I mean, like if you want to have as a bigger part of the design, 3-tap and a 5-tap, then will you be able to use one file?
Yes, you can still use one file, because all that matters is when you instantiate it, right? When you instantiate it, you're given the option of overriding a parameter. So as long as you have written your code in such a way that if the parameter controls everything, and overriding that parameter would change the design the way you want it, so then you can just keep one single file and just as you instantiate, override the parameter and instantiate it. Does it make sense?
Yeah.
Okay. So yeah, this is about parameters and why they're useful and what's your physical significance. So let's look over some more syntax. So essentially, before we declare the ports, but now we need to actually define what they are. So what does that mean is, like, now we are telling, for example, these ports over here are inputs and these ports are outputs, like this port is an output. Then we need to tell what is the type of the port. So in this case, we are defining the type as a wire type. I'll go over what are the different types a little later on in the tutorial. And then since we are working on FIRs and we're working in a lot of numerics, we can even define these as signed operations, just so that it does signed arithmetic instead of unsigned arithmetic. And finally, we can define the dimensions of these basically, let's say, wires. So there are 2 dimensions which you can operate in Verilog. So there are the dimensions which are before the name of the wire. So let's say in this case it is this coef width -1 down to 0, and the dimensions which are after the name of the wire, that is this 0 to n taps. So what is the difference between the two? So if it's actually before the name, we actually call these as packed dimensions, and if it's after the name, we call it as unpacked dimensions. Now, what is the physical significance of a packed dimension versus an unpacked dimension? So the way you think of it is that packed dimensions are those dimensions which are logically together as like a bus. So for example, if you're working on a breadboard, right, think of it that you have a bus of wires all working as like a entire set and not as individual wires themselves, right? You've seen like those multicolored rainbow buses which you can connect, right? So that's kind of what you think as a packed dimension. An unpacked dimension just means that you have multiple of these wires. So though each one is independent of the other, but within itself, the packed dimensions are all connected to each other, right? So the unpacked dimension is what you truly think of as an array in like your other programming languages, just like element 1, element 2, element 3. And the packed dimensions are what you think as the width of the bus. Like taking let's like put these numbers in. For example, what we are saying is that we have what say 3 coefficients of 8 bits each, right? If you just substitute these values in like these parameter values into this definition. So that's about the packed dimension and unpacked dimension. So just one important thing which I'll point out is that Verilog has a 0 base numbering system. So all the numbers start with 0, and also it's not like other like something like Python where you have to go 1 plus. It's like if it's an 8-bit number, so that means it will count like the counts would be 0, 1, 2, 3, 4, 5, 6, 7. So we would define an 8-bit number as 7 down to 0, right? You actually define the 2 endpoints of the bus. So an 8-bit number would be 7 down to 0. Yeah, these are just like common things which are a little different, which people may make mistakes. Yeah.
So when you mentioned the difference between packed and unpacked
Yes.
Dimensions, so the unpacked you can manipulate like any single, like for example 0 to n minus 1, you can manipulate it independently, something like that, or like in the packed you cannot manipulate like any individual.
So you could manipulate both independently. It's more to do of what it represents physically. So like let's say for example you are considering a memory location, right? So the packed dimension you can think of as contiguous memory in your device. The unpacked dimension is just like a separate memory block altogether. So all the packed dimensions indicate is that you're defining a memory in like you're defining your variable in a contiguous memory kind of way, or you're defining it as a bus which is meant to interact as a whole. An unpacked dimension is saying that each one is an individual element and you cannot work on it as a whole. So for example, in the packed dimension, if I want, I can assign all 8 bits at one time. But in the unpacked dimension, I can't assign all 8 at once. I need to actually assign it one at a time because there's nothing which says the whole set together as a whole represents anything. Does that clarify your question?
Yeah, and one follow-up question. So
Yeah.
like when I was like looking at the declaration of the packed and unpacked, so packed you go from like top 7 down to 0, and for unpacked you go from the low 0 to the max. Why is this any convention or like?
This is a convention and just style. Actually, you if you want, you can go in both cases. You can go from 0 to this thing, but this is kind of just a convention. I think I would say more of just like a coding style kind of a thing. There's no reason why you should go from top to bottom. It's just that whatever style you ultimately choose, you need to stick to that, right? Because if you choose like let's say from higher to lower. So when you're actually working in your codes, even let's say if you want to access only the first 4 bits of the 8 bits, right? you would say 4 down to 0 and not 0 to 4. Let's say like that. Yeah.
So, and one more follow-up question, I just missed that. So, when you mentioned, when like the question I asked, like if I want to declare another module with tabs number 5, I would need a different module, right?
No, you use the same module, you just override the parameter when you instantiate it.
Could you like provide an example or like anything? Like
I don't think I have an example of how to override parameters, but maybe I can just point out in the one where I show instantiation. Okay, so let's continue. Yeah, and probably the last thing which I forgot to mention is that when you have multiple dimensions like unpacked dimensions and packed dimensions, the order of it is little weird. So normally we would think that it'll be left to right, but in reality, what the unpacked dimensions come first and then the packed dimensions. And you can kind of understand why, right? Like the higher level dimension would be the number of wires, and then the lower level dimension would be the bits in the wires. Okay. So now that we actually defined a module, now we'll see how we actually instantiate it. So how do you build a larger module? So let's say you have a top level module which calls this FIR and it calls some sort of memory block and different things. So in this case, we would actually create an instantiation like this. We would have the module name. We would give a unique name to this instance. So let's say in this case, I've called it IDUT, but you could say IFIR1, IFIR2, and so on. And then you'd make all the connections. So what this kind of a code represents is that the one on the left with the period is saying what is the name of the wire within the module, and the one on the inside the inside the like the circular braces is saying that what is the wire at the top level. Essentially, you're trying to, the way you think of it is like if you have a breadboard, you have your IC like which you place on top of the breadboard. The one on the left represents what's the name of the pin on the IC, and the one inside the bracket is saying what is the external wire which you connect to it, right? So these are all wires at the top level, and these are all wires within the module. So you're just making a wire connection between these two blocks. So this is about instantiation, and even though it's not shown here, like I mentioned before, when you actually instantiate this design, you could override the parameters. So there's a particular syntax to which you need to, which you can easily Google online and see how to override parameters during instantiation. But here essentially I could create two instances of the same module and with just different parameters. So for example, I can say this is FIR1 with these parameters, and then this is FIR2 with these parameters. I can even create two instances with the same number, with the same parameters as well, if I connect it, let's say, to a different set of inputs. So like I said, modules are essentially building blocks, and how you put it in and connect it to each other is up to you as a designer. Right? Is this part clear to everyone? Okay. So one of the most important things which I tell everyone when they like first get into Verilog is concurrent execution. So if you have not come across a hardware description language before, you're very used to the fact that everything you write is a sequential operation, right? The first line of your code is going to be the first thing which is executed. That is plainly not true in Verilog. So Verilog, the way you think of it is that you're kind of designing actual hardware blocks, right? So if you're, let's say, designing a AND gate, or let's say a multiplexer, and would the multiplexer wait for the functionality of the AND to happen before it does its own functionality? No, right? The multiplexer is completely independent of the AND gate. The AND gate is completely independent of the multiplexer. What that means in terms of code is that every line of your code is a concurrent operation. So the way you imagine that is that any line you write within your module or design, imagine would it still work if it was occurring at the exact same time as every other line, right? Which is literally the definition of hardware. The only exception is that when you have these statements called always blocks, which we will go over a bit more in detail later, So anything within an always block is sequential, but different always blocks are again concurrent, right? The way you think of it is that an always block is just a block of code where you can write a more complicated logic so that you don't have to break it down into the bare metal code like your behavioral code. So within that will be sequential, but then you can define as multiple always blocks, and then those different always blocks will be parallel to each other. Yeah, and the best debug hint I can give you is that if your code depends on the sequential nature of it, most likely it will break when you design it in Verilog. So now, what are the different types of, what are the different data types? So there are two classical data types, which is wires and reg, which is like based on the Verilog standard. And there are a lot of differences of when you use wires, when you use reg. If you have used Verilog before, feel free to use it. But if this is your first time working with Verilog or system Verilog, I would highly recommend using logic. It saves you a ton of trouble to figure out when do you use a wire, when do you use a reg, because a logic can use whenever you use either of them. The whole purpose it was brought in was to completely eliminate all the confusion involved in when to use what. Okay, so the way you can think of it is like your logic is your go-to declaration for almost anything in this in Verilog. Essentially, what logic is defining is that it defines a variable as a 4-state value. So a 4-state value is it has the value 0, 1, x and z, where x means that it's a indeterminate condition. That means the design cannot determine whether it's a 1 or a 0. Z means that it's an unconnected wire. So the way you think of it is as a high impedance, right? If you have a design but you do not connect a pin to anything else, that will be like a high impedance line. So that's the Z value. So this should be good enough to work with the designs you have, and logic should be a go-to for all of this. So now the other thing which you need to keep in mind, which still is a separate thing, is blocking versus non-blocking operators. So there are basically two kinds of ways you can do assignment in Verilog, either use the blocking operators or non-blocking operators. So as the name blocking suggests, is blocking just says that till it completes the assignment, it will block the execution of this device. The way you think of it is that this is kind of a continuous assignment statement. What kind of logics use continuous assignment statement? Like, for example, logic gates. An AND gate will not care what any other system is like. Whatever input it gets, it will give you the AND of those two inputs and then give you an output. A non-blocking operator, just ignore the order here, it should be whatever's in the figure here. A non-blocking operator essentially means a deferred assignment. So it figures out what the output should be, but it delays the assignment to some point later in time. So this is entirely designed to model flip-flops, right? So if you think about a flip-flop kind of captures a value at an edge and then assigns that value slightly after that edge happens, right? So that's kind of the physical significance of it, and it's entirely used to design flip-flops. So a simple question of when to use blocking or non-blocking. Did you intend to design a flip-flop? If yes, then you use a non-blocking, else just use a blocking operator. That should kind of simplify when and where to use it. And the kind of differences which come about is you can actually see in this small snippet over here. So for example, in this case, if we are actually doing a blocking operator, what it's doing is that it's capturing the value of Q1 on the positive edge of a clock, which you can imagine is a flip-flop over here, right, a D flip-flop. But because you're saying Q2 is equal to Q1, Q1 has got the value of D as well as now Q2 will get the value of Q1. So the way you think of it is that it just becomes a direct wire connection. If you actually did both of these as non-blocking operators, what you're saying is that these non-blocking operators will only occur at the pause edge of clock. So at the first pause edge of clock, it would capture the value D into Q1, but then Q1 would not have been updated yet. So Q2 will still see the old value of D and it does not change. On the next cycle, Q2 will see the new value of Q1 and then it will change. So essentially this is equivalent to stacking two flip-flops back to back. So hopefully this kind of gives you the difference between blocking and non-blocking, and kind of one of the most common reason people's designs actually fail in Verilog. It's one of the most common mistakes you can make. So now that we look at blocking, non-blocking, we'll kind of look at what is the different kinds. So we can have, what are the different kinds of logic we can have. So the first kind is called combinatorial logic. So combinatorial logic just means that any logic which does not preserve the state of the system. The simplest example you can think of is logic gates, right? An AND gate, an OR gate, let's say an XOR gate, right? They do not need to know the memory of the system. All they need to know is what is the current set of inputs. So, and again, this way you can actually define it in three different ways: structural, register transfer level, and behavioral. So let's look at what these actually look like in terms of code. So let's take the simple case of a multiplexer, right? So you can represent the Boolean logic of a multiplexer with this diagram, where S is the select line and A and B are your two inputs and Y is the output. So if your select line is 0, you would want the output, like you'd want the input A to be seen on the output. If the select line is 1, you'd want the input B to be seen on the output. So now if you were to represent this as a structural code, you would actually build it from the first principles. You would actually design this NOT gate, you design an AND gate, you design the AND gate for A and S bar, you design an AND gate for S and B, and you define finally an OR gate for like adding these two, like ORing these two values. So whenever I use bar in logic, it means like it's a negated version of the input of that signal. So as you can see, it can be quite cumbersome to build up on these blocks. Like if you can imagine like building upon these gates as you get more and more. So a billion gate design would mean that you literally have to design a billion gates like this. So next level we go to something called the RTL level, or you can even call it the data flow level. So in the data flow level, you essentially abstract it away to your logical operations. So for example, if you want to do this kind of a multiplexer, you can say something like NOT of S and A or S and B, right? You literally represent this your Boolean logic equation in legal Verilog syntax, and that is your RTL level, right? We have this keyword assign, which is just saying that assign the output of this logical operation to this register. Does that make sense? Or rather transfer it to register, hence register transfer level. So yeah, and the last case is behavioral. Like I said, at behavioral level, you just want to abstract away entirely the design, like you do not want to care about the semantics or how the tool will implement it. You don't even care if the tool actually implements it as these 4 gates. Maybe it implements it in a completely different way. So in that case, we just define it at as a high level abstract. The most simple thing you can think of in a multiplexer is you just have a case statement for each of the values of the select line. So in this case, what happens if the value is 0, and what happens if the value is 1. So in this case, if the value is 0, your output is going to be A. If the value is 1, your output is going to be B. Right? And this is just like the general syntax of what a combinatorial block is. So here I've used something called always at rate star, but again to avoid confusion, Verilog has actually introduced something called always comp, always underscore comp. So the simple way to think of it is that if you want to end up implementing combinatorial logic, you just use the always COM block and put whatever logic within that. Verilog will, like system Verilog will ensure that the design you implement will be combinatorial. So in the last slide, I basically showed about a simple block like a multiplexer, but you do not need to be limited by that. You can in fact design much more complicated blocks using behavioral. So maybe if you were learning Verilog 20 years ago, or maybe not even 20 years, maybe around 10, 15 years ago, you would actually need to physically implement, let's say if you're making a multiplier, you would actually need to physically implement a multiplier. That would mean like you need to actually draw like, okay, what are the partial products? You need to sum up all the partial products and then get an output, and then you'll have all these complex multipliers, complex adders. With time, they realize that's not a good use of a designer's time, so they kind of moved away from that system where now they can even, I think every operation probably except divide can be done right at the behavioral level. So for example, if you just want to do a multiplier, you just have to do like the first value times the second value. So yeah, they use the asterisk key for the times operation. So, and the other thing is that if you're working with sign numbers, you can just you can like typecast the values to sign. This is very similar to C, C++, just to ensure that when you do your multiplication, you're doing, let's say, a signed multiplication. So yeah, so this basically makes your life a lot easier when you need to implement something like a multiplier or an adder. So now that we actually implemented, let's say, these basic blocks in the combinatorial world, now let's see what is the sequential world. So sequential world is essentially flip-flops, right? We are implementing some kind of memory within our system. So the key syntax for a flip-flop is you say always underscore FF for a flip-flop. Again, this is telling the tool that whatever logic I'm going to design right now is going to be a flip-flop. So now if you want to design the most basic element of a flip-flop, what are the different things you need? You need some kind of a clock pin to actually tell on what edge does this flip-flop work. You need some kind of a reset pin because a flip-flop is a memory, right? Before the very first value, what is the value of the flip-flop? So to tell that we need, or to basically bring the flip-flop to a stable state, we usually have a reset pin to say, okay, make the flip-flop go to the stable state at this time. And in terms of code, this is kind of like you can think of as like a boilerplate for a flip-flop code. So you have always FF. So you're saying that this flip-flop is a positive edge triggered flip-flop. So it works on the pause edge of your clock. And this is an asynchronous flip-flop because it's also being triggered by the negative edge of the reset, right? So the difference between a synchronous flip-flop and an asynchronous flip-flop is a synchronous flip-flop means just that all your operations happen on the clock edge, including a synchronous reset. So this would mean that in terms of code, this block would just not be here. But if it's an asynchronous reset flip-flop, it means that as soon as a reset comes, the entire design gets reset. Yeah.
The D bar is already pre-computed before going to the else bar, right? Because if it is the output, then it will be two flip-flops, right? Or like there is some circular connection or something. In line 65. D bar is pre-computed.
So this won't exactly be how the flip-flop will be. I've just, in reality, this code would, like you said, create two flip-flops, right? But I've just written it here to represent what you normally view as a flip-flop. But yes, the code for this is actually implement two flip-flops. Usually you do not implement both the positive and the negative logic. You just implement whatever logic you want. And the tool kind of figures out which one to use, right?
Within the always block and the non-blocking statements, they are executing in parallel or in sequence?
Yes, they're all executing in parallel. So you can actually imagine that these two lines are executing in parallel.
Even if I declare as a combination block?
No, if you declare as a combinational block, so generally you wouldn't want to put a non-blocking in a combinational, and I'm not sure, but I think it may give you an error also nowadays. I don't know if it gives an error now, but I think that's one of the intentions, that you should not have flip-flop logic within combinational. Similarly, you should not have combinational logic within flip-flop. So yeah, they're meant for two different purposes. So whenever we think of non-blocking, we always think of the flip-flop operation. So this would generally mean that these two are working in parallel.
What I meant, like the blocking statements within a combinational or will be executed in parallel, right? All the blocking.
No, those will be executed in series, in sequential. So that's the one exception I said, right? Within an always block, it executes one line at a time.
So in that case, could you please go the two slides back? I had one question. Here, yeah. So the behavioral description where we are actually examining each of the case statement one by one, right?
Yes. So the way you could think of this is that, how do I put this? In reality, maybe the compiler may, or like when you simulate it, it will imagine it one by one. So that is what you call a priority case. But usually when you write a complete case like this, the synthesis tool will assume the fact that you meant it to be a multiplexer. So then what it would do, it would literally treat, it would assume that all your conditions are mutually exclusive, which it is in this case, right? So that is the true case of a multiplexer.
So I have to be very careful to complete the case statement.
Yes, so that's where this default key comes in here. So default, let's say for example, if this was a 4-bit, a 2-bit select line, right? So there can be 4 possible values, and let's say we're only interested in 2 of the values. So for 2 values, we will define the outputs, and then we will have a default case to say, okay, if the other 2 came, what should the output be?
In case I do not complete the case statement, what is there going to be error?
It will build a latch. Because the moment you have an incomplete case, what it assumes is that you have some kind of memory in your system, right? So if that, let's say the case 1, the select line 1 comes, since that's no option, it needs to hold the previous value, and holding the previous value implies memory, so it tries to implement a latch.
That's an error in the design.
In system Verilog, it will be an error. So because if you use an always com block, it will actually be an error, because you have a separate block called always latch if you want to implement latches. But if you just implement it in pure Verilog, which is like always at the rate star, it will just assume you wanted a latch and it will make a latch. Because that is actually a legitimate and legal way to design latches. So yeah, in Verilog, it won't know what's your intention, but in system Verilog, it will know the intention, because you will say what is your intention, whether it's combinatorial or a latch. Right? Okay. Yeah, the next thing which we're going over is finite state machines. I'll maybe just briefly go over this, because maybe you can look at it on your own time, but essentially how you would design a finite state machine is that we have something called a 2 always block or a 3 always block design. What that essentially means is that in a finite state, so what exactly are finite state machines? So if you have taken like the digital, like the 4000 level digital course, a finite state machine essentially tells what are the states of your design, right? Like, is it in an idle state? Is it in a, let's say, power on state? Is it in addition, multiplication, different states like that? And then in different states, you kind of say that, okay, what are the kind of operations which happen in those states? A finite state machine is just a top level control block which says, how do you transition between these states, and what control signals do you drive based on these states, right? So for example, in this kind of a block, we, based on the condition, so if you're currently, let's take one case, if you're in the idle state, and let's say we get these 2 inputs, we determine what is the next state, as well as let's say what is the output signal we want to control. So in this case, we are saying that the next state will be the, let's say, power state, and then we want to drive the output as a 0, right. So a lot of what FSM design in Verilog is taking an actual FSM chart and then trying to implement that in Verilog looking at the different conditions. So for example, in this case it was if A is equal to 1 and B is equal to 0, transition to the power state, which is exactly what is the condition we have written here. So as you can see, behavioral code is literally describing whatever you see in the diagram.
What is it, local param keyword?
Oh, okay, yeah. So the difference between parameter and local parameter is that parameter is you can think of it as a constant of the block or like a physical property of the block which can be overridden from the top. A local param is the constant of physical characteristic of the block which cannot be overridden. Right? So maybe some things you want the designer on the top to say, oh, instead of 3 tabs, let me have 5 tabs. Right? But I don't want the designer to say change the states of my FSM, because the states of the FSM have to be these states only. They change the state of the FSM, the whole design may break. Right? So that's kind of where like the local param versus params. Okay. Yeah. Oh, I think I just saw one mistake in the file. Let me just quickly correct it. Okay, so now now that we actually have all of these things, right, we need to find a way to test our design. So what does that mean is that I won't go into too much detail, but we have actually, I think Professor has uploaded a folder to your Canvas page, which is like which is called FIR. If I'm not mistaken. So that gives an example of a test bench and the design, the code, the FIR design which I've shown thus far, and kind of gives you how like the different scripts you need to run it. So one of the scripts you have is this thing called a run file. So that essentially tells you how you would run a simulation. So what that means is that essentially in Verilog or rather in system Verilog, once you have the FIR, right, how do you know whatever you designed is correct or if you made a mistake? So that's essentially where a test bench comes into play. A test bench is whose entire goal is to see whether the logic works without caring how it works, if that makes sense. Say you have a very complicated filter which does a lot of operations, or or you have some kind of a communication protocol which needs to send out some kind of packets which has a lot of pre-processing to do. If from the top level you just know what is the input and what is the output, kind of that's the only thing which you care about, right? So essentially a test bench just does that. It throws some input into your design and then it just checks the output what it got back and says, is that the correct output? So let's say for example, if I'm implementing a filter, I know for this sequence of inputs what should be the output of the filter. And all I do is I just feed in the input, get the output from the block and just compare it like one item at a time against what is my expected value in the filter. Right? So one thing about this course is you probably don't need to design very elaborate test benches. Since we are working mostly with DSP systems, one of the best ways you can actually do it is, let's say you're implementing an FFT. What you can do is you can have some kind of a like a predefined input which you design in something like MATLAB or Octave or Python, and basically save that as a text file. So then in your test bench you can feed in the input into your Verilog block one at a time, get the output and store that in a text file, and then just read that text file into MATLAB and see, okay, did I get the right value? Right? Because that will usually be a lot simpler than trying to write the logic for that in a test bench itself. But let's say, for example, if you were working in, let's say, purely digital domain, it maybe makes sense to just design the entire logic within the test bench itself. So is testing clear to everyone? and what you need to do. So a lot of what you need to do in the test bench is already provided in your in that module, in the folder which we have given you. So go through that code. The main difference between a test bench and a design is that a test bench does not care for synthesizability. So one thing which I've talked a lot about is how we take a piece of code and translate it to hardware. A test bench does not need to care about that, right? Because in reality, you're never going to implement a test bench. So you can write it in as abstract a way as you want, in a completely, like, let's say one single, they have something called a program block, which is essentially a sequential block where you can write line by line of code, and it will operate it as one line at a time. So you can write a test bench in as C, C++, or Python-like manner as you like. Okay, and it will mostly accept everything which, as long as it's within it's a legal syntax of system Verilog. Yeah, and the other main difference between a design and a test bench is a test bench can actually keep track of time, whereas a design cannot. So what do I mean by keep track of time? So but then you will be imagining, okay, all hardware is something physical and it keeps track of time, right? But hardware usually keeps track of time as by using external sources. Like for example, we have the clock module here. So it basically counts the number of clock edges, and based on that, it decides like how much time has elapsed. But in the case of test bench, you can literally say how much time. So you can make write statements like along the lines of, okay, wait 5 nanoseconds, then drive this input. Wait 10 nanoseconds, read the result, then drive this new input, things like that. So you have a lot of flexibility when it comes to test benches. So I won't go exactly how do you run it, but then if you actually look in the folder, there's something called a run file, which is essentially what is the command lines you need to put into your terminal to run this, or you can even source that file directly. Yeah. So yeah, now let's look at 2 examples. So hopefully we should be able to finish on time. So I'll basically walk you through 2 examples of how you would actually design something in Verilog. The first is a simple 3-tap filter. So if you think of the microarchitecture or like the circuit level design, this can be a representation of what it is. So you have a data input. It passes through these 3 delay elements to get these delayed versions of the data. You multiply those with the coefficients to get, let's say, these multiplier outputs, and then finally you add these outputs together to get the final result. So now how would you actually define this? And I've kind of defined here what would be the widths of all of these. So the data widths here would be 8 bits, these coefficient widths would be 8 bits, and then the number of taps is in this case 3. So that's why you have 3 tap here. And then finally, we are saying the output data width is 20 bits, right? So this final output is going to be 20 bits. Yeah.
Not related to Verilog, but so there will be a minimum output width, right? Like around 16.
Yes. So if you multiply that's right. If you multiply 2 8-bit numbers, you will get 16 bits. So, but as a designer, you have complete control. So if you want the final result to be again 8 bits, you can do that, but then you need to add some logic to actually handle that, right? So this looks basically very similar to what you saw before. Essentially, we have created these parameterized definitions of your data so data, these are actually your delay elements. So for the number of taps, you have that many delay elements in your system. Like you mentioned, when we actually multiply 2 numbers, the final output width is going to be the sum of the 2. So in this case, we have here data width plus coefficient width. And then once we actually have the output, we have something called output data width, which we are converting this multiplier output to this new data width, and we have this data width for this coefficient. And then in the unpacked dimension, we have essentially defined the number of taps, because we can imagine that for each tap, these are 3, let's say in this case 3 tap, these are 3 individual operations. So if we want to implement these delay elements, we can actually use something as like a code like this, which is like a parameterized shift register. All it does is it takes the input data into the first element of the shift register, and then we can use a for loop like this to shift the elements from one register to the, like from one delay element to the next, right? So here is really the power of parameters, right? Because you can now you can see with this code how we can represent an like how many ever taps that you'd like. Similarly, for multipliers, for each particular tap, we multiply the data and the coefficient. Again, we can use a nice for loop to iterate through all the taps to do the multiplications. Similarly, we can use another for loop to implement the adders. So to add the, so if you remember this thing, it basically adds the same index multiplier with the previous index result, right? With the exception of the very first case, which needs to just be the first result itself, and every other case will be the same index multiplier output plus the previous adder's output. So now you can see like how we can actually design the entire 3-tap filter with a very simple blocks once we have actually parameterized the entire design. So all of these codes are available to you. It should be there in the folder which the professor has provided, and you can go over in more detail, and I'll also share this presentation with you later. So that's the simplest block which you're going to work with in this entire course. So let's look at a more typical block which you may come across. So maybe it's something like this. So if you remember what has been posted recently in your homework, I think it's problem 5 or problem 6, you need to implement a Verilog for a module like this, right? So how would you actually go about doing this? So the way we do it is like we kind of break this problem down into its different parts. So for example, the first thing which we would want to implement here is we'll implement these delay elements in this design. So the way we think of it is that this is kind of like a flip-flop. So each delay element is a flip-flop. So to implement 2 delay elements, we would essentially need 2 flip-flops. So that is why we have, let's say here xd is 0 to 1, and then you have xd of 0 is just taking the value of x, so that's creating 1 delay, and xd of 1 is taking the value of xd 0, so this is creating another delay element. So what we are actually doing here is like we are literally, when we have these variables here, what we are doing is we are just physically naming these wires here. So you can imagine that this wire in between these 2 delay elements, let me just get the pointer. So you can imagine this wire in between the 2 delay elements is just going to be the xd0, and this wire after the second delay element is going to be xd1. Does that make sense? So that's literally the physical representation of the variables in Verilog. They represent the wire connections between these different blocks. So now that we have actually defined these blocks, maybe the next thing which you would want to define is this multiplier and this adder, right? So similarly, so in the previous case we knew these were flip-flops, so we defined it as always ff. So now that we know that a multiplier and adder are combinatorial, we'll define it as an always com block, and essentially we write a behavioral code for it. So if you, in this case, we want to multiply the value of xd0 with a, so you write xd0 times a, right? As simple as that. But like you mentioned, when you actually multiply 2 values, you actually get twice the width as an output. So that's why you can see this multiplier full is saying here twice the width. It is then your job as a designer to actually figure out which of these bits you're going to keep. So for example, we want the final multiplier out to be also, let's say, the same width as before. So then Verilog as a language does not know how to interpret these bits. It just thinks of these as bits, it just treats these as bits, and it just does a multiplication. You give it as an integer, you give it as a floating point, you give it as anything, it's just going to treat it as bits and it's going to multiply the 2. So what I mean by you need to decide how you interpret it, right? So For example, one of the most common ways which we write in this course, or which you will use in this course, is something called a fixed point representation. So what a fixed point representation means is that you're just saying how many bits are going to be part of the integer and like integer portion of your number, and how many bits are going to be the fractional portion. So for example, if you have an 8-bit number, you can maybe decide that, okay, I'm going to have the first 2 bits being integer and the last 6 bits being a fractional part, right? So now when you multiply these two, let's say this sequence, right? So you're going to have totally 16 bits on your output, but because you have defined it as 2 bits integer and 6 bits fractional, in your new output you're going to have 4 bits integer and 12 bits fractional. Does that make sense? The way you think of it is that if you multiply 2 integer numbers, let's say 2 2-bit integer numbers, you get a 4-bit integer number, right? But from Verilog's point of view, it does not know any of this. From its point of view, it just multiplied 2 8-bit numbers and it got a 16-bit number. So then it is your job as a designer to actually figure out how you want to interpret it. So now if I still want an 8-bit number, I would take the lower 2 bits of the integer and the upper 6 bits of the fractional. So that will still be in the same representation as my inputs. Does that make sense? Right? So in this case, in your 16-bit value, you would take essentially from bits 14 down to, in this case, it would be bit 14, essentially 14 minus 8. Right? So it will be down to bit 6. Does that make sense? And in this particular case, I've actually used the value of 1 and 7, like 1 bit integer and 7 bits fractional. So that's why I'm basically taking as the width, instead of width minus 1, I'm making it width minus 2 down to width minus 1. So I'm just taking the 15th bit all the way down to the 9th bit. And finally, when you implement an adder, you just directly implement xd1 plus x, right? Again, we just write it in terms of behavioral. So the next major block which you're actually going to see is these switches, which you will see throughout your homeworks. So when you're actually implementing a switch, like if you see a kind of a diagram like this one here, I hope is the pointer being seen? Yeah. Okay. Yeah. So all this is saying is that this implements a multiplexer. So whenever you see this diagram, you know you're going to implement a multiplexer. And when you see codes like this, like 2L and 2L plus 1, 2L essentially says how many like inputs are there to your multiplexer. So if let's say it was 5L, that would mean there are 5 inputs to your multiplexer. And 5L plus 1, 5L plus 2 and so on would just say what are the outputs for those particular inputs. So here in this case you have a 2-input multiplexer. So this is like 2L plus 0. So you can say when the multiplexer is 0, you're going to take the output of this multiplier, and when the select line is 1, you will take the output of this adder. As simple as that. Now the question is, how do you decide what's the select line? Whenever you see something which is of the order, which is something like this, like 2L, 3L, 4L, the first thing which you should think of is implement a counter. Because all this says is that you're designing a periodic select line, right? Which has a periodicity of, in this case 2, if it was 5L means it has a periodicity of 5. So from a Verilog point of view, that just means implementing a counter which counts up to 5. So when the counter value is 1, you do the 5L plus 0, counter value is 5L plus 1. If the counter value is 2, you do 5L plus 2 and so on. So does that make sense? So I hope this part is clear, because this is a thing which you will keep seeing throughout this course. And like how we did before, we can just repeat that step for this new adder, new multiplier and new switches. So hopefully with this kind of an example and working through this, and with you having the slide, you should be able to work out the problems in the homework. So I think we have about 5 minutes left, so I'll quickly wrap this up. So the last thing which we have is once we actually design everything, we need to synthesize it so to see how good our design is. So in this particular case, what synthesis does is that it converts your Verilog code to actual physical gates and flip-flops and building block, like the different kinds of building blocks. And once you do that, you can actually report the different characteristics of the design. Let's say, for example, what is the area of the design, what is the power of the design, and what is the let's say timing, like what is the slack. So slack, you'll hear the word slack a lot. All the word slack means is that if you have defined a clock period for your design, let's say I've defined a clock period of 10 nanoseconds, but the actual design, the critical path of the design, I guess you've come across critical path, right? Let's say the critical path of your design is 8 nanoseconds. So all that would mean is that you would have a slack of 2 nanoseconds. It's the difference between the clock period and your critical path time. A negative slack would mean that your critical path is greater than your clock period, which essentially means that your design is failing, right? So if you have a positive slack, means you're within your clock. If you have a negative slack, you are basically your design is failing. So in a lot of problems, we have asked you to report the critical path time. So how you essentially get it is that you would see the slack of the design, you know the clock period of the design, and from that you can calculate what is the critical path time. Does that make sense? And I won't go in a lot of detail about over these slides. These are literally step-by-step instructions. So whenever you actually get to implementing your design running synthesis, just follow the steps in this, and if you have any questions, feel free to email me. I'll be more than happy to help you out and help set it up, because this is just a one-time thing which you need to set up at the beginning. And from what I've seen in past years, as long as you follow these steps as is, it should work straight out of the bat. Okay? And similarly, you need to place your inputs in a certain hierarchy or a directory structure, which is again defined over here. So make sure that you just follow that hierarchy structure when you implement or synthesize your design. Okay. And yeah, this slide just tells essentially how you would run your synthesis tools. I won't go over exact details. Again, these would be things you just try it out here and see how it works, see if it's working fine. And from your point of view, as when you're designing this, there will be a reports directory. So there will be a reports directory which will tell what is the area, what is the power, and what is the, I think it's called timing, the last report. So whenever we ask you to report area, report timing, or report power, it would mean like after you run synthesis, open the reports directory and then just read those reports to see what is the final area, timing, and power. Okay, so what is the critical path time, what is the area, and what's the power of the design? Is that part clear to everyone? Okay, that's about it, I think, and we are just in time. Maybe have a minute or so for questions. Does anyone have any questions about any of this?
How do we submit the Verilog assignments?
I think there should be a link on Canvas. Is it not there yet?
No, I mean, okay, so we just have to submit it on Canvas.
Yes, you just have to upload your files to Canvas. That's it. I think you just need to submit the Verilog codes. You don't need, and you need to report the other numbers, if I'm not mistaken. Yeah. So if there's not a link, I'll talk to the professor and I'll add a link later.
For the homework number 1, we should submit it through Canvas. The deadline is today.
Oh, actually, I think. Let me just check. I think professor sent an email about this, right?